Next, definition of bounded function. Function f of x is called bounded function on some interval, say closed interval a comma b, if mod of f of x is less than or equal to some constant k for all x in closed interval a comma b. Next topic, properties of continuous function on closed interval a comma b. Now there are three properties of continuous function. Let us see all three properties one by one. So suppose f of x is continuous function on closed interval a comma b, that is, it is continuous at each point of this interval. Then it implies that first property is f of x is bounded on closed interval a comma b. That is, what is the definition? Mod of f of x will be less than some constant for all x in closed interval a comma b. Second property, if f of x is continuous on closed interval a comma b, then f of x attains its bounds mean supremum value of f of x and infimum value of f of x. Largest value of f of x and smallest value of f of x. So if function is continuous on closed interval a b, then that function attains its bound on that interval a comma b. What is the meaning? That is, there exist some numbers small c and d in closed interval a comma b such that f of c, this value is supremum value of f of x, and we write it like this. And f of d is infimum value of f of x, and we write it like this. So function attains supremum value at the point c and it attains infimum value at d. This is a second property. one more property of continuous function. If f of x is continuous on closed interval a comma b, then f of x takes every value between f of a and f of b. This statement is known as intermediate value theorem. Next definition, uniform continuity of f of x. F of x is said to be uniformly continuous on some interval, say closed interval a comma b, if for any epsilon positive number of our choice, there exists another positive number delta such that mod of f of x1 minus f of x2, this difference is less than epsilon whenever distance between x1 and x2 is less than delta, and this holds for all points x1 x2 in closed interval a comma b. Now this epsilon is a small positive number of our choice. So that is, we select epsilon as 0.1, 0.01, 0.001 and so on. So selecting smaller and smaller values of epsilon means two values of the function becomes approximately same whenever distance between x1 and x2 is less than delta. In that case, these two values become approximately same. So suppose this is your interval a comma b. If you select 2 points x1 and x2 such that difference between x1 and x2 is less than delta, in that case difference between the values of the function at x1 and x2 is very small, or the two values of the function at these 2 points are almost equal. The 2 points can be anywhere in the interval a comma b. So suppose these are the two values of x and their distance is also less than delta. So whenever this distance is less than delta, difference between the values of the function at x1 and x2 is less than epsilon. We can take x1, x2, these 2 points anywhere in the interval. If their distance is less than delta, then difference between values of the function at these 2 points is very small, or the two values are almost same. So this is a definition of uniform continuity. A note on uniform continuity. Suppose this is a number A, this is a number B. So what we learn in the definition of uniform continuity, whenever difference between x1 and x2 is less than delta, difference between values of the function at these 2 points x1 and x2 is less than epsilon, and epsilon is a small number of our choice. So suppose this is one interval of length delta 1, and this length delta 1 is less than delta which we have used in the definition of uniform continuity. So delta 1 is less than delta. So this interval which is of length delta 1 means its length is less than delta, and if you select any 2 points in this interval, then by definition, when the difference is less than delta, difference between values of the function f of x1 and f of x2 is very small. Suppose next interval is this, and its length is delta 2, and delta 2 is also less than delta, and whenever length is less than delta, and if you select any 2 points in this interval, if its length is less than delta, then from the definition of uniform continuity, difference between values of the function at these 2 points is very small, or it is less than epsilon. Continue like this. Suppose third interval is there with length delta 3, and delta 3 is also less than delta. Then if you select any 2 points in this interval, then by definition of uniform continuity, difference between values of the function at this 2 points is also less than epsilon, and so on. Suppose the last interval is nth interval. This is nth interval, say delta n, and its length is less than delta, and therefore if you select any 2 points in this interval, then by definition of uniform continuity, difference between values of the function at these 2 points is also less than delta. So this is the first interval, this is a second interval, this is a third interval, and last is, say, nth interval. So n is some finite natural number. So what we observe is that if f of x is uniformly continuous function. On closed interval a comma b, then for any epsilon positive number of our choice, we can divide closed interval AB into finite number of subintervals. Say n subintervals. As shown in this figure, we can divide closed interval AB into finite number of subintervals, say n subintervals, such that what we have seen, that if you take any 2 points in any one of these subinterval, then difference between the values of the function at these 2 points is very small. That means it is less than epsilon for all x1, x2 in the same subinterval. If x1, x2 are in the first interval, this inequality hold. If x1, x2 are in the second subinterval, same inequality hold, and so on. If x1, x2 are in the nth interval, then same inequality hold, that is difference between values of the function at these 2 points is less than epsilon. So we use this statement when we prove first property of continuous function. Next, second note, if f of x is continuous on closed interval AB, then f of x is uniformly continuous on closed interval a comma b. So we want a closed interval and continuity of the function on this closed interval. If it is continuous on closed interval a comma b, then it is also uniformly continuous on that interval, closed interval a comma b. Actually, this is a theorem and we will not prove this result because this is not included in our syllabus. So we use both of these statements when we prove properties of continuous function. So let us prove first property of continuous function. If f of x is continuous in closed interval a comma b, then it is bounded in that interval. So given that f of x is continuous function in closed interval a comma b, therefore it is uniformly continuous in that interval. Now f of x is uniformly continuous in closed interval a comma b, therefore for any epsilon, a positive number of our choice, we can divide closed interval a comma b into finite number of subintervals. Say n subintervals. Such that mod of f of x1 minus f of x2, this difference will be less than epsilon for any 2 points x1, x2 in the same subintervals. Let these n subintervals be, first is a comma a1, so suppose this is a number a, first interval is a to a1, second is a1 to a2, third is a2 to a3, and nth interval is an minus 1 to an, and this is our last number b. So let these n subintervals be, first is a comma a1, second is a1 comma a2, third is a2 comma a3, and so on. Last is an minus 1 to an, but an is b. We now prove that f of x is bounded on each of this interval. So consider the first interval a comma a1, and let x belonging to a comma a1 be any number in this interval. So this is the first interval a comma a1, and x is any number in this interval. Now from equation 1, suppose this is our equation number 1, which says that for any 2 points x1, x2 in the same subinterval, the difference f of x1 minus f of x2 is less than epsilon. So we use this equation 1 for each subinterval. Let us use this equation 1 for the first subinterval a comma a1. Now in this interval, we first apply equation 1 to these 2 points a and x. So therefore from equation 1, mod of f of a minus f of x is less than epsilon, because a and x are 2 points in the same subinterval. Similarly, apply equation 1 to these 2 points x and a1. So again from equation 1 we get mod of f of x minus f of a1 less than epsilon, because x and a1 are points in the same subinterval. Next we apply equation 1 to these 2 points a and a1. So again from equation 1 we get f of a minus f of a1 less than epsilon. So suppose this is equation number a1, this is equation number a2, this is equation number a3. Now we have to prove that function is bounded on the first interval a comma a1. Now consider mod of f of x, where x is an element from the first interval a comma a1. So it is equal to f of x. Now subtract f of a and add f of a. Now there are two terms. First is f of x minus a and second is f of a. So it is smaller than mod of first term plus mod of second term. Using the property of modulus, mod of a plus b is less than or equal to mod a plus mod b. Now first term, mod of f of x minus f of a, from equation a1 is less than epsilon, and second term mod f of a we keep as it is. Thus mod of f of x is less than k1 for all x in the first interval a comma a1, where what is k1? K1 is a constant, epsilon plus mod of f of a. F of a is value of the function at first point of the interval. So by definition, f of x is bounded on first interval a comma a1. Now we prove that f of x is bounded on second interval. Next, we prove that f of x is bounded on second subinterval a1 to a2. So suppose this number is a1, this number is a2. Consider any point in this interval. So let x belonging to second interval a1 comma a2 be any point. Now again we use equation 1. Equation 1 says that on any subinterval the difference between values of the function at any 2 point is less than epsilon. That is, if you consider these 2 points a1 and x, then from equation 1 mod of f of a1 minus f of x is less than epsilon. Similarly, difference between values of the function at these 2 points will also be less than epsilon. So f of x minus f of a2 is also less than epsilon, and third pair A1 to A2. F of A1, F of A2, this difference is also less than epsilon. Suppose this is equation B1, B2 and third is B3. Therefore, mod of f of x, where x is any point in the interval a1, comma a2. So mod of f of x is equal to, now subtract and add f of a1. a1 is the first point of this subinterval. Again there are two terms, so it is less than or equal to modulus of first term plus modulus of second term. Using the property of modulus, mod of a plus b is less than or equal to mod a plus mod b. Now from equation B1, difference between these two values f of a1 and f of x is less than epsilon. So this difference is less than epsilon plus f of a1. So therefore mod of f of x is less than epsilon plus mod of f of a1. Now we try to replace f of a1 with f of a. So how to replace? Let us see. Suppose this is equation number 2. Now mod of f of a1 is equal to f of a1 subtract f of a and add f of a. So again we have addition of two terms. So therefore f of a1 is smaller than modulus of first term plus modulus of second term. Now look at the equation number A3. Where is equation number A3? So in equation A3, mod of f of a minus f of a1 is less than epsilon. So from equation A3, mod of f of a1 and f of a is less than epsilon plus second term mod f of a as it is. So this is from equation A3. Now put this value in equation 2. We get, therefore from equation 2 mod of f of x is less than epsilon plus mod of f of a1, and mod of f of a1 is less than epsilon plus mod of f of a. That is, mod of f of x is less than 2 epsilon plus mod of f of a. So thus we have obtained f of a in place of f of a1. This is a fixed value of the function at first point of the given interval ab. So thus mod of f of x is less than k2 for all x in the second interval a1 to a2. This point belongs to the second interval, where what is k2? k2 is 2 times epsilon plus mod of f of a. Therefore, by definition, f of x is bounded on second subinterval a1, a2. So we have proved that function is bounded on the first interval, it is bounded on the second interval. Similarly, we can prove that mod of f of x is less than, what is the inequality for the first subinterval? We have shown that mod of f of x is less than epsilon plus f of a for all x in the first subinterval. For the second subinterval, we have shown that this is less than 2 epsilon plus mod of f of a, and so on. So for the third interval, we will get 3 epsilon plus mod f of a for all x in the third interval a2 to a3. Mod of f of x is smaller than 4 times epsilon plus mod f of a for all x in the fourth interval a3, a4, and so on. For the nth interval, it will be n time epsilon plus mod of f of a for all x in nth subinterval is an minus 1 to an, but an is b. It means that f of x is bounded on the first interval, it is bounded on the second interval, it is bounded on the third interval, function is bounded on the fourth interval, and so on. Function is bounded on the last subinterval, nth subinterval, an minus 1 to b. Thus, f of x is bounded in all n subintervals of closed interval AB. Therefore, f of x is bounded in closed interval AB. So whenever function is continuous in closed interval a comma b, it is bounded on that interval.